We are dealing with periodic classification, right? In this, I was telling you, these highlights in the previous class. Remember, it is not about placing these atoms or elements or metals and non-metals in rows and columns. It's not that simple as we think, right? You must understand there are some rules, principles that are driving this periodic table to frame in a proper way. And let me tell you, one of the highlights which I was actually quoting in the last class is basically, remember, it's not so trivial. It in fact stimulates research. So it's not as simple that someone has given you 130 elements in your hand and you're just going on to put them in rows, in columns, and then frame it as a periodic table. Absolutely wrong. Absolutely trivial thinking it is. You must understand that it is so much serious over here that I would like to use these wordings that it stimulates research. Now, what do you mean by this stimulating research? Mind you that tomorrow, if you are finding an element, say 20 years from now, you find an element 20, 30 years from now, or even more than that, then that element's place is fixed in the periodic table right now. So it is actually leaving a scope of research for you. Go out, find elements, and if you find an element, I have a place for you in the periodic table, right? So what I mean is basically understand that you have 7 periods and 18 groups in the periodic table, right? 7 periods and 18 groups in the periodic table, and let me tell you that the 7th period itself is incomplete, right? And also remember that I was telling that each period is a shell. Each period basically is a shell. And we were told in atomic structure, I was telling you that you have infinite number of shells. So we have infinite number of what? Periods, you must understand. And the 7th period itself is incomplete. When the 7th period itself is incomplete, then that leaves the scope for you to go out and find out elements based on the way the periodic table is framed. And when you find out that element's position is absolutely fixed right now in the periodic table. That is what I meant by it stimulates what? Research, you must understand that. Right? And we don't discuss about what they have attempted, the history of framing of periodic table. We are not attempting that, right? We are just discussing the modern periodic table in which you have, you must consider each period is a shell, or I can say it's an orbit. Each period is a shell or an orbit which is proposed by what? Bohr, which is designated by the principal quantum number 1, 2, 3, and it goes on to infinity. So you can expect that infinite number of what? Periods which are available. But till now, I think the 7th period itself is incomplete, leaving you a scope for what? Finding out elements from here on, and then your position is basically fixed in the periodic table, which surprises me even at this level, you must understand. So anyone who's actually getting into the periodic table must understand that it's not simply someone gave you 130 elements in your hand and you are placing them with a pencil and a scale and you are drawing it. No, absolutely not. You must have that broad thinking that it stimulates research. And the second one is each period is a shell, leaving you a scope, because 7th period itself is incomplete, leaving a big scope, huge scope for you to discover further elements, and I have a position for you in the periodic table. You must understand that, right? The other thing what I would like to say, you have n number of elements, approximately 130 elements for you in the periodic table, 130 elements in the periodic table. And then if you ask me a simple question, what is the difference between all these elements? Tell me one difference. You can have n number of differences, but what is the basic difference in which the other differences are a function of, right? If you ask me one simple difference between the 130 elements in the periodic table, right, each having different physical and different properties, then I would like to say it's simply atomic size. It's atomic size. So I can tell you that, the chemical or physical properties of these elements, basically depends on the size. You must understand that. So the modern periodic table the modern periodic law, you must understand why there is a basis for why a particular element, particular group is showing a set of what properties, then I would like to write a periodic law which says that the chemical and the physical properties are functions of atomic number, are functions of atomic number Z. And what is atomic number? The number of protons that are present inside a particular element or an atom, that can be called as atomic number. And all the physical and chemical properties are basically functions of what? Atomic number, or synonymously I can tell you that atomic size. You must understand it, right? If this is the case, that means I'm indirectly telling you the basis for framing the periodic table is not atomic mass as proposed by earlier people like Mendeleev, where they get lost in somewhere while framing in the middle of the periodic table. They were unable to frame further. For them, I think that's an obsolete thing. But I think the modern periodic table, which we were discussing, proposed by Moseley, I think the framing has been done on the basis of what? Atomic number. You must understand that. So the prime thing here, if someone is asking you what is the basic difference between all the 130 elements that are available in the periodic table, then you say that it's all about atomic size. Someone is asking why the fluorine is so much reactive, why the chlorine is so much reactive, why the sodium is so vigorous, why the D block elements are less vigorous. And all these must be primarily must be a function of what? Atomic size. You must understand that is a basic difference. Well, also I was telling you something about periodic properties. Periodic properties are those properties which repeat itself at regular intervals, like a law of octaves. You must understand this. So they repeat itself at regular intervals in a period, hence can be called as what? Periodic properties. Mind you, you have 7 periods and 18 groups in the periodic table. And if you wanted to know the geography of the periodic table, then I can say that you have the S block, the alkali and alkaline earth metals, to the left hand side of the periodic table. To the right you have the P block, which is actually 6, because P can accommodate only 6 electrons, S can accommodate what? 2 electrons. In between you have D, which is total of what? 10. And then 2 series are taken from the main frame of the periodic table. They also belong to the periodic table itself for a decorum, right? For a convenience or a decorum to be maintained in the periodic table, they are taken outside and put it down as lanthanide series and actinide series. That is how the geography of the periodic table is. You must understand. So basically, overall, if you see what I mean to say, that the basic difference of all these elements in the periodic table is atomic size. You must understand. It's all about the atomic size or the atomic radii, what we call determines the physical and chemical properties. That was the introductory discussion which I was making in the previous class, and I was just briefing you. At the same time, I was also telling you, when you actually take atomic radii, if you actually see the first periodic property, I can say this is periodic property number 1. Now, what is a periodic property? People who are listening to me, a property that repeats itself at regular intervals in a period can be called as what? Periodic property. You must understand this, right? Regular intervals, like the law of octaves, sa re ga ma pa da ni sa. It is repeating, right? Similarly, it's like a law of octaves. So similarly, I think a property that repeats itself at regular intervals can be called as what? A periodic property. In that thing, the first periodic property which I was discussing is atomic radii. I was discussing about atomic radii. Now, when everyone has an idea, because atom is spherical, and what is atomic radii? If you ask, anyone can actually tell us that it's a distance between, it's actually basically distance between, right, it's distance between nucleus to the outermost shell. Nucleus to the outermost shell. That distance is basically what? The atomic radii. But remember, you can only understand better when you understand that electron itself is a shell. Shell is no different from electron. Both are same. I can tell you with conviction, because if there is no electron, no shell. No electron, no shell. So electrons, shells, orbits, or non-radiating paths, all these are synonymous. You must understand. So when I say distance between the nucleus to the outermost shell, I'm basically referring even to the electron. Well, this seemed to be fine because everyone can understand that's how atomic radii must be defined, because it is the nucleus to the outermost shell. But I encounter so many problems sticking on to this definition, because what you're telling me is take an atom, then you cut it off, and you take a scale and measure from the nucleus to the outermost shell. That's what you're basically telling me, which operationally is impossible to do it. It's absolutely impossible to do it, because what happens is when you propose this definition, this seems to be absolutely ideal and absolutely not operational. And I was telling you this because, first of all, taking an atom and isolating it itself is a difficult thing. You cannot isolate an atom. And assuming that if you isolate an atom also, finding the exact position of the electron outside the nucleus is almost impossible, says Heisenberg's uncertainty principle. Right? And the third thing is, if at all you have found out the position also, then understand that electron has an irregular boundary. It's like a cloud. It has an irregular boundary. And also, since it is a cloud, it has a diffusing property. It will be diffusing and relaxing from the nucleus. You must understand that. If such is the case, first of all, you are not able to isolate an atom. That's number one. Number two, you cannot find position. Number three, electron has an irregular boundary. With all these, what I find is this definition is absolutely ideal. This definition is absolutely ideal. You must understand this, right? Absolutely ideal. Then what we are supposed to do is we have to switch for an operational definitions. And that's what I'm actually telling you, operational definitions of what? Atomic radii, because we have an issue. But it's not your choice or my choice. I'm compelled to do it. It's not a choice. It's a compelling thing for me. Because what happens is, even I wanted to stick to this atomic radii definition, right? But I can't do that because I cannot isolate an atom. So any measurement which is ideal, any measurement, if you can do it, if someone can do it for me, right, that will be if you stick to this, then you will be having no error at all. No error at all. You don't have an error at all. You understand that? Because it's absolutely ideal. Now, if any deviation, it's compelling, as I'm claiming it's compelling for me, then if you try to deviate from the idealistic definition, then I think errors creep in. The errors will be creeping in. Since I said it's compelling, there is no other way. We have to live with the error. We have to live with the error. So if that is the case, then understand that in all these operational definitions, in fact, all the operational definitions, if I quote it, operational definitions of atomic radii. Operational definitions of atomic radii, that is, first of all, I call this to be covalent radius, right? And two, I have van der Waals radius, and the three, if you see, I call this to be metallic radius, and to four, it's ionic radius. You must understand this. It's ionic radius. So, since I have an issue with the idealistic definition of atomic radii, I'm actually proposing 4, not 1. It's not 1. Because, it's not my choice. It's so compelling. Why 4 instead of 1? It would have been better when I have taken an atom and cut it off and then measure it up from the scale, from the nucleus to the outermost orbit. Things have been done there itself. But I think we can't do that. So we are actually proposing what? 4 operational definitions. Why 4? Let us understand this. First of all, the biggest issue is, when you can't do an idealistic thing, when you get into these 4 operational definitions, then all these will have errors. All these will have errors because you have deviated from the idealistic mode. So all these will be having errors, and we have to live with error. If that is the case, then the common sense is suggesting that basically you need to minimize what? Error. You must be minimizing error. Since we are living with error, error is not a good thing for the measurement. So I think everyone must minimize the error. And to minimize the error, what we are doing is, in now single atom isolation is difficult. It's basically difficult. Single atom isolation is difficult. So what you do is, then take two atoms. They take two atoms. Now, you suppose this is atomic radii. So you're supposed to take an atom, write one atom, but you can't do that. You can't do that. So what you're doing is you take two atoms. When you take two atoms, error is induced into it. Error is induced into it. Now what we're trying to do is minimize what? Error. When you wanted to minimize error, the two atoms, what you do is you have to basically ensure two atoms, and you basically ensure the atoms to be as close as possible, right? Because one atom you can't do it. You're taking two atoms, and when you take two atoms, right, they are actually what? Inducing error. But at least to minimize the error, I wanted to ensure the atoms are very close to one another. Well, in chemistry, understand that atoms are very close to one another only when they participate in bonding, and no other circumstance will compel them to be as close as possible. You must understand this. So atoms are very close to one another when actually they are participating in bonding. So the close as possible, and this situation is only when atoms are actually what? Bonding. You must understand, they are actually bonding. The atoms are close when they are actually participating in what? Bonding. You must understand. Well, if that is the case, as a chemistry student, you must understand that bondings are not one. You have various types of bondings. That's why, I propose 4 operational definitions, not one. You're not completing it by just replacing, one atomic radii definition with one. Remember, instead of one atom, you have taken two atoms. When you have taken two atoms, error is in your life, and we must be minimizing the error. And we wanted to minimize the error. We have to ensure that the two atoms are basically close to one another. And such situations where atoms are close to one another is basically when the atoms are participating in bonding. And in chemistry, we don't have one single bonding. You must understand the nature of bonding differs. And some participate in covalent bonds. Some participate, some do not participate at all, like inert gases. They don't participate in bonding. Then in such cases, what to do is basically go for what? Van der Waals radius, right? And then you must understand you have metallic radii. You have metallic radii for metals, because some participate in metallic bonds where the atoms are supposed to touch each other, right? And then you have ionic radius for people who are ions and radicals. You must understand this. So it is a spectrum of what? Nature of bonding which you will find. So operational definitions replaced for an idealistic definition of atomic radii cannot be one. They are rather 4, because the only situation when atoms are close to one another is when they participate in bonding, and bondings are not 1 but 4. Now what we will do is, before we get into the trend of atomic radii in the periods and in the groups and their consequences, let us define what is covalent radius, what is van der Waals radius, what is metallic radius, what is ionic radii. You must understand. Let us actually define each one of them, right? Shall we? Yes. Let's take operational definition 1 now. Let's define it. Let's first define it, and then if any formula are there, let's get acquainted with that. Then we will go for the trend, how the atomic radius basically varies in the periods and groups in the periodic table and their consequences. You must understand this. Now, what is covalent radii? Covalent radii is basically an operational definition because we are unable to find out atomic radii. This seem to be absolutely ideal, right? And remember one point which I wanted to highlight about this. This has error. This has error. This is not an absolute value, but I'm actually compelled to take a covalent radius, you must understand, right? Because we are taking 2 atoms here. Mind you that. So don't celebrate about having a covalent radii, but remember that it has what? Error, but we have that error has been minimized. That is a simple case what I'm quoting. Now, what is this covalent radius definition? Right, it is half. It is basically half. Mind you that. If someone is asking what is covalent radius, it's basically half. I would like to underline this. It's basically half. It is half. It is half. Right? Covalent radius is half. The internuclear distance, it is basically half the internuclear distance between atoms. Mind you, it is half. Basically, someone is asking you what is covalent radii. Tell them it is half. Now we'll ask you half of what? Half of the internuclear distance. It's basically half the internuclear distance between atoms basically participating in covalent bond. You must understand this definition. Here are some things which I need to highlight it for you. Right? First of all, understand that covalent radii is not an absolute radii as the case of atomic radii is. Covalent radii involves 2 atoms. When it involves 2 atoms, I think error has crept in already. The error has crept in already, you must understand. When the error has crept in, then I think this will be having an error. And then what is the definition? It is half the internuclear distance, right? Is basically covalent radii. If you actually see, it is half the internuclear distance between atoms. It's not atom. It is atoms. That means you are involving 2 atoms. Actually, we are supposed to take only 1 atom in your hand, cut it off, take a scale from the nucleus to the outermost shell, which is absolutely not possible. And we are taking 2 atoms. So the error has crept in. When the error has crept in, it is atoms participating in covalent bond. Covalent bond. Well, let me tell you 2 things which are for your remembrance, right? When you're pursuing science throughout your life. Well, someone is asking you, how do you judge whether you have a covalent bond or an ionic bond between atoms, right? Let me tell you that if a bond is between a non-metal and a non-metal, if a bond is between non-metal and a non-metal, then the bond is essentially covalent. Then the bond is basically what? Covalent, essentially covalent. Mind you that. Now, how much degree covalent it is, that is a separate part of discussion. But mind you that a bond between a non-metal and a non-metal is essentially what? Covalent. You must understand this, right? And you have a covalent force between these 2. At the same time, if the bond is between a metal and a non-metal, is essentially ionic. You must understand this, right? So how do we judge whether you have a covalent bond between atoms? And the bond between a non-metal and a non-metal is basically what? Covalent, you must understand, right? So we are discussing covalent radii, and here is the definition before you. And let me read and highlight few of the things here. It is half the internuclear distance between atoms. I would like to say atoms. It's not 1 atom. We are taking a situation of a covalent bond where 2 atoms are involved. Participating in covalent bond. You must understand. So what I will do, I will get a pictorial representation of this definition for a better understanding. You must understand, and I draw the attention of everyone. Watch carefully here. If I can give you a pictorial representation of, this definition, it looks like this. Watch carefully. If this is the hydrogen atom, right? And if this is another hydrogen atom, mind you, we are actually finding atomic radii. If we are finding atomic radii of hydrogen, which is a non-metal. We are finding atomic radii of hydrogen. Normally, in normal circumstances, if you wanted no error in this measurement, then you're supposed to take hydrogen atom in your hand, cut it off, from the nucleus take a scale and then find it out the distance to the outermost orbit. Then you're supposed to get atomic radii, which is not possible, as I was screaming from the beginning of the periodic table that it is impossible, it is absolutely ideal, you can't isolate an atom. So in such cases, you are compelled to take two atoms. The moment you take two atoms, error is induced. Now the only thing left for you is ensure that these two are as close as possible. And the situation where these hydrogen atoms are as close as possible is when they participate in bonding. So if you see, once they participate in bonding, they are actually little bit closer this way. They can't overlap with one another. There's closure, and there is redistribution of the entire electron clouds inside. So I can say this is the nucleus, and if you see, once they participate in bonding, this is how the hydrogen molecule looks like. With these two nuclei, right? So this is basically a hydrogen molecule. Right? So what is telling, once you have hydrogen atoms participated in covalent bond, then he is take the half of the internuclear distance. This is the internuclear distance. That's the internuclear distance, and make it half. This is covalent radii. That's covalent radii, you must understand. And this internuclear distance, in our words, we call this to be bond length. We call that to be bond length. The internuclear distance is nothing but what? Bond length. You must understand. So what is happening here? Is basically, to understand the subject clearly, right? Understand that we are trying to find out atomic radii of hydrogen. Normally, how do we do that? Take hydrogen in your hand, hydrogen atom in your hand, which is not possible. But still, if you think it is possible, take it out, cut it off, and then find the distance. Things are over. But you can't do that because you can't isolate an atom at all, first of all, in the first place. Right? Then we are taking two atoms. When you take two atoms, you have to ensure they are very close to minimize the error. And the closest distance is when they are actually participate in covalent bond. And I'm sure that it will be covalent bond because hydrogen is a non-metal. The other hydrogen is also a non-metal. And the bond between non-metals is essentially what? Covalent. You must understand this. So once the bonding is finished, I think this is how the hydrogen molecule will be looking at, and then it is half the internuclear distance between the nuclei, and you make it half. This is covalent radius, and the internuclear distance is nothing but bond length, right? So it is basically like this. So it implies that basically covalent radius is nothing but bond length by 2. Bond length by 2. This is bond length. Bond length by 2. And this will be a question in the exam. I would like to highlight. That's a question in the exam. What he will do in the exam is basically you find out bond length and he will give you covalent radius. So bond length is basically twice of covalent radius. You must understand this. So it's otherwise the reverse also might be asked. He will give you covalent radius and ask bond length, it will be twice. Our covalent radius is bond length by 2. That is the first question you must understand. So covalent radii is only applicable for people who are participating in what? Covalent bonding in the periodic table. Now it's a common sense that, not every atom in the periodic table will participate in what? Covalent bonding. So we can apply this covalent radii, or we can determine the covalent radii only for people who participate in covalent bonding. And who are the atoms that participate in covalent bonding? Basically, they should be non-metals, and for all the non-metals who are participating in bonding, we determine covalent radii for them. You must understand that. And non-metals are essentially placed to the extreme right of the periodic table. To the right of the periodic table, that is the P block, right? To the left are metals, and the D block you have what? Metals. So you must understand it is towards the right, like hydrogen, chlorine molecule, hydrogen molecule. This we can find out covalent radius. Hydrogen, chlorine, right, bromine, all these you can actually find out what? The covalent radius, because they are all non-metals participating in covalent bonding. So that is the first operational definition which I would like to say, and I would like to read it out once again before I get into the second part, right? Watch carefully here. So it's basically half. It is half the internuclear distance between atoms participating in covalent bond. Is so clear? So this is only applicable for what? Elements participating in what? Covalent bonding, you must understand. And those are basically non-metals. That is how the pictorial representation is. And this is the formula which he will be asking in the exam. Right? Now, what about other people who participate in metallic bonds, who don't participate in bonding at all? How do you deal with them? And what about metals, because they are by default touch each other? Because we require atoms to be touching each other, right, to minimize the error. If that is the case, metals do touch each other because they are solids. Most of them are solids. You must understand, and solids, you don't have atomic spaces at all. How do we deal with them? Right? Let's go for the second one, that is van der Waals radius. You must understand this. Shall we go for the second go for the second atomic radius? Yes. And here is what is the first one, that is covalent radius. Then what we do, we go for the operational definition number 2. And I draw the attention here. And I am discussing now, it's basically van der Waals radius. It's van der Waals radius. You must understand. Now, why van der Waals radius? As I said, will covalent bond can be used for finding out radii of the entire periodic table? No, absolutely not. We cannot, because the essential thing is you must participate in what? Covalent bonding. You must understand this. And in the periodic table, not everyone participates in covalent bonding, because the essential condition is you should be non-metals. And let me tell you, there are basically cases where some people don't participate in bonding at all. Some do not participate in bonding at all. You must understand. And I'm referring to inert gases. I'm actually referring to inert gases. What to do? If they don't participate in bonding, the question of you taking 2 atoms also is what? Is vague. Now, we can't take 1 atom, and we cannot have 2 atoms participating in bonding. What shall we do? Is the issue. What shall we do is the issue. For such people, I think for such atoms which do not participate in bonding, I propose to you the van der Waals radius. You must understand this. Right? Van der Waals radius, you must understand. Now, it is extremely difficult for people who don't participate in bonding, and then you're considering 2 atoms and doing it is a difficult proposition. Let us say this, you must understand here. Right? Now, what this van der Waals forces is basically, van der Waals radius is basically an operational definition. Operational definition instead of what? Operational definition 2, which was replaced for atomic radii. Right? And this is basically done basically for atoms who do not participate in bonding. Now, it's covalent bonding. Fine, you are close to one another. Well, in every operational definition, I am supposed to take 2 atoms. In covalent radii, it's a covalent bond, which is a common thing. They have participated in bonding. Fine. We have minimized the error and we are very happy. But what about people who don't participate in bonding? What about people who don't participate in bonding? You must understand this. And the case, it is the case of what? It is basically the case of what? Inert gases. The case of what? Inert gases is an issue. Right? The case of inert gases is an issue. Then what we are supposed to do? What we are supposed to do? Well, I would like to explain, but let me actually define what exactly is van der Waals radius, and I draw the attention of everyone, and I would like to highlight each and every point in the definition. That's what is the key. Now, what is van der Waals radius? What is van der Waals radius? I say it is basically, it is half. It is again half. It is basically what? Half. Half of what? Internuclear distance. Right? It is again half. It is again half of internuclear distance of adjacent atoms. Adjacent atoms. Now, it's slightly confusing. I draw the attention of everyone. It's slightly confusing. Right? Watch carefully here. It is half. It is again half. Half of what? Internuclear distance. It is half of internuclear distance of adjacent atoms. The nearby atoms, adjacent atoms. I have not finished it. Of adjacent atoms of adjacent molecules, you can actually cut off here, but I think van der Waals radius is also applicable to some of the molecules, so I just extend it. It is half the internuclear distance of adjacent atoms of two adjacent molecules, and I am writing this, watch carefully here, between which van der Waals forces exist. Between which van der Waals forces exist. Now let me tell you that bond is a force. You can't tell stories. What is a bond means you give one, I give one, we'll both share it and put it at the center and live happily. That's a story. Let me tell you that. A bond is a force. A bond is a force. And in the previous covalent radii also, if two atoms are bound by a force which is called a covalent force. If covalent force binds two atoms, we call that to be a covalent bond. If van der Waals forces is binding two atoms, adjacent atoms of two adjacent molecules, we call that to be what? A van der Waals radii. It's a van der Waals force. Right? I'll explain what is van der Waals force. But let us go and read closely what is van der Waals radius. Observe carefully. It is half the internuclear distance of two adjacent atoms. You can actually stop it here in case of what? Inert gases. But if you wanted to apply this van der Waals forces to even hydrogen, which you have done it, and check out the relative issue with van der Waals radius and hydrogen, then I think it's a better way to do it. So I wanted to extrapolate it and then watch. It is half internuclear distance of two adjacent atoms of two adjacent molecules between which van der Waals forces exist. What I will do is I draw it, right? I give a pictorial representation of this, and then we will see what is van der Waals force. Then you can understand better, right? Well, I draw a diagram for you, right? Watch carefully. I'm actually comparing this, right? I compare this with what? Hydrogen molecule, and I draw the attention of everyone. Watch carefully here. Now, for the hydrogen molecule, this is for the hydrogen molecule. This is for the hydrogen molecule. Now, covalent radii, if you see covalent radii, then it is somewhat like this. This is what I said. This is the hydrogen molecule. These are the two nuclei, because hydrogen molecule has two atoms of hydrogen. That is the internuclear distance which I actually put it. And if I make it half, this distance is nothing but the covalent radii. This is what we were telling earlier. This is what we are telling earlier. Now, I just wanted, out of curiosity, I just wanted to know what will be the van der Waals radius of hydrogen. I wanted to know. Now, why I wanted to know, that also I will reveal it. But in case, suppose if you wanted to find out van der Waals radius for the same what? For the same what? Hydrogen molecule, for the same hydrogen molecule, then how do you draw it and fit this definition into that? Now, people will ask a doubt. Sir, you already have a covalent radii definition for hydrogen. Why are you interested in van der Waals radius for what? Hydrogen. This is ridiculous. Because already we are suffering with an error. Already we are living with an error. Are you not increasing or decreasing the error by proposing such a thing? Well, exactly that is what I wanted to know. Exactly that is what I wanted to know, which one to consider. That's what it is. And in which case the atoms are very close to one another. That means indirectly I'm telling you which force is stronger. Is it the covalent force or the van der Waals force? And I would like to consider the force which is stronger, because in the stronger case, the atoms are close to one another. And let me check out which force is stronger, is covalent force or the van der Waals force. That is the issue. Right, if that is the case, van der Waals force for the same molecule, if I can draw and fit this definition, then observe carefully here. Observe. This is the hydrogen molecule. This is one hydrogen molecule, mind you. One hydrogen molecule. Then I draw another hydrogen molecule. Right? Similar. This is again hydrogen molecule. And what he is telling is, right, let me put it, it is half the internuclear distance of two adjacent atoms. Well, this molecule has two atoms, that molecule has two atoms. And these are the adjacent atoms, you must understand. And he's asking us to take the internuclear distance between two adjacent atoms, not this and that. Two adjacent atoms of two adjacent molecules. Look at this. Two adjacent atoms of two adjacent what? Molecules. Two adjacent molecules between which the van der Waals forces exist. Now I'll tell you what is van der Waals forces, but let me put the definition first. Let me again fit this definition into what I'm telling. So it's basically internuclear distance is this, and he's asking us to make it half, and then this is van der Waals radius. So it's internuclear distance between what? Two adjacent atoms of two adjacent molecules between which the van der Waals forces exist. That's what is van der Waals radius. So it is several questions are cropping up. In fact, I question myself on your behalf. Well, the first question is, first of all, why are you taking hydrogen molecule? Because for hydrogen you have already told covalent radii. Why are you doing it? That's number one, right? Well, that itself is my question also, why I'm doing it. Well, if I can do it, if I can apply van der Waals radius, right, then I'm able to see which force is stronger. Which force is stronger? Is the van der Waals force stronger or the covalent force stronger? Then accordingly, I think the force which is stronger, that radii I would like to consider, and even I wanted to know how bigger or how much error has crept into by the weaker force, that is nothing but the van der Waals force. I just wanted to know on relatively, I think how much big is what? Van der Waals radius than the covalent radius. I just wanted to compare it. So you need not take van der Waals radius for hydrogen, because when you have covalent radius, because covalent force is stronger than what? Van der Waals force. You must understand that's an obvious thing. But why I'm doing it? Because I just wanted to know how much bigger is that? How much bigger is that? You must understand, right? How much it is, right? So let us see. And I want to redraw this diagram again and again fit this definition. And I want the attention of everyone. Redraw this diagram for you, comparing covalent radii, van der Waals radii for hydrogen atom, right? For hydrogen atom rather. Right, if I compare both the diagrams, then this is the first case, that's the first case, this is the internuclear distance, and this is basically the hydrogen molecule. And if you take the internuclear distance, make it half, This is covalent radius. This is nothing but the bond length. And then I think you have covalent radius is basically bond length by 2. This is a done deal. That's the covalent radius. This is covalent radius of hydrogen. That is a case 1. Now if you see covalent, and if you take the van der Waals radius of hydrogen atom, then he says take 2 adjacent molecules. This is molecule 1. This is molecule of hydrogen. This is another molecule of hydrogen. Mind you, 2 molecules, right? So there are totally 4 atoms involved here. So this is molecule of hydrogen. Then he's telling, take internuclear distance of the 2 adjacent atoms, 2 adjacent atoms of 2 adjacent molecules between which the van der Waals forces exist. So you have to ensure that the molecules are coming into the clutch of the van der Waals forces. You're not taking it separately. You must be having that van der Waals forces, that you have to ensure, right? And then he's telling this internuclear distance, right? This internuclear distance, and make it half. This radius is basically the van der Waals radius. You must understand this. Right? So I have compared this with this. Now, first of all, why, as I told you, this question crops up again and again. Which one is correct? Which one you need to take? We want to take that, or you want to take this, right? There is always a question. So you understand that which one is we must be taking it. It all depends on which one is giving a minimized error. Minimized error. And for your information, it's actually prudent. It's actually prudent or wise on the part of anyone to consider covalent radius for hydrogen atom, and I write not van der Waals radius. It is only for your importance and the curiosity to know relatively how much bigger is van der Waals radius, but otherwise no one should consider van der Waals radius for hydrogen. It's only for our understanding. So why we don't do it? Because van der Waals forces are weaker than covalent radius. You must understand, they are weaker. They are weaker. When the van der Waals forces are weaker, then I think the atoms are not close to one another. They are actually falling apart. That situation we don't want it, because already we are living with error and we are supposed to minimize the error. So what I'm telling in all, that I can simply say that van der Waals radius is greater than covalent radius. Now it is up to you whether you consider hydrogen atom, for hydrogen atom you consider van der Waals radius or covalent radius. And it is very much prudent on your part not to consider van der Waals radius, just for comparison, just to understand that, to reconfirm, rather reconcile and be satisfied that van der Waals forces are weaker than what? Covalent forces, you must understand. So my final conclusion for you is basically consider what? Covalent radius for hydrogen and not what? Van der Waals radius. Now what is a van der Waals force? Let me explain this. What is basically a van der Waals force? Let us understand, shall we? Now what we will do, say this is basically, I'm comparing a covalent radius of hydrogen with van der Waals radius of hydrogen. You need not compare. This is only for a theoretical importance. You must be only considering covalent radius for hydrogen, because a covalent force is stronger than van der Waals force. When the force is stronger, the atoms are actually close towards one another. In van der Waals radius, they are apart, right? So considering what? For what? Hydrogen, van der Waals radius is ridiculous. Don't do that. It's prudent actually to consider what? A covalent radius and not that. And why you have done this? Then I have done this because just I wanted to know how much magnitude it is greater. And I would like to conclude by telling you that van der Waals radius is of course greater than what? Covalent radius. You must understand this. Now what is this van der Waals force? Now if you're not applying, if you're basically not applying it for hydrogen, so what is it used for? What is it used for? Well, there are certain elements in the periodic table which are praised to the last group, to the last. That is inert gases. That is nothing but the inert gases, right? What they do is they don't participate in bonding. They don't participate in bonding. When they don't participate in bonding, then how do you deal with them is the issue. right? What I will tell you is observe carefully now. Observe carefully. I draw the attention. So first of all, I'm warning you not to consider, basically not to consider, absolutely don't consider van der Waals radius for hydrogen. It's better to consider what? Covalent radii, because that gives you less error. Even though both give error, but I think the hydrogen will give you what? Lesser error, because the covalent force is stronger than what? Van der Waals force. Now what is this van der Waals force, and why are we, to whom it is basically applicable? And I draw the attention of everyone. Watch carefully here. Right, let us see what exactly is a van der Waals force. Well, I draw some technicals into you. Watch carefully. Watch. Suppose if I take an inert gas atom, I'm taking it. Watch carefully here. Basically, this is better used for inert gases. Inert gases which do not participate in bonding easily. They don't participate in bonding easily. I don't make a sweeping statement that they don't participate in bonding, because we have compounds of what? Inert gases available these days. Yes, not easily relatively to the other atoms, right? So for them, I think the better we use van der Waals radius. Now, well, I take an inert gas atom. Watch carefully here. This is an atom, right? And when this is an atom, what is the understanding? The understanding is you have a positive charge here, that is a nucleus. Positive charge here, that is a nucleus. And then you have the negative charges. These are the negative charges, right? That is how the atomic setup is. That is how the atomic setup is. And how do you actually view this setup, if you ask me? Well, if you actually see, I see this in this fashion. I say the positive charge, mind you, the positive charge is in equilibrium with negative charge. I can say the positive charge is basically in equilibrium with the negative charge. You must understand this, right? Well, atom is neutral. Atom is basically neutral. How do you actually tell people that it is neutral? Then a normal answer, what we get it is, if the number of positives are equal to number of negatives, then the atom is neutral and not charged. Well, I differ from this. Well, in a classroom, actually, if you see, in a classroom, the number of boys and number of girls are equal, right? But still the class can be charged. You must understand this, right? Now, what is happening here, when I am lecturing, the boys are all towards one side and the girls are all separated towards the other side. And I am lecturing, still the class is charged. Number of boys are 30, girls are also 30. I am lecturing, but still the class is charged, because all the boys are looking towards girls, or the girls are looking towards boys. You have separated it. The class is charged. So the best way to avoid disturbance in a class is basically ensure that there is equilibrium. That's why sensible people in the classroom will be actually distributing the students in this way: one boy, one girl, one boy, one girl in a class, and the class is now neutral. You must understand. So, if someone is asking me that how do you consider atom to be a neutral, the common answer what we get it is the number of positives equal to number of negatives. Yes, of course, it is an answer. But not necessarily, because understand that you still can have charge on the atom provided you don't have this equilibrium. So the better way to explain people why is an atom neutral is basically understand that the positive charge is in equilibrium with what? Negative charge. So they are distributed in such fashion, as I gave an example, a boy and a girl and a boy and a girl, and the class is neutral and I am able to deliver the lecture. If you don't do that, all boys towards one side, all girls towards one side, each looking at each other, and my lecturing and dumping the concept would be a difficult thing, but the class is charged. So from next time, if someone is asking how do you say the atom is neutral, then it is positive charge is in equilibrium with what? Negative charge, right? If that is the case, then I draw a similar atom. Well, I draw a similar atom, right? Here is a positive charge. All the negative charges are in equilibrium with this, right? All the positive charge is in equilibrium with what? Negative charge. This is the case where the positive is in equilibrium with negative. Similarly, the positive is in equilibrium with negative, and both are neutral. This is neutral. That's a neutral atom. And this is also a neutral atom because you have an equilibrium between the positive charge and the negative charge. It's neutral. Now what I'm doing, I apply some pressure because this is a gas. This is a gas. Inert gases, right? It's gases. All are inert gases. So those are gases. So what I will do is I will apply some pressure. When I apply some pressure, the atoms are very close to one another. The atoms come very close to one another. When they come close to one another, then one electron cloud, this cloud, will interact with this cloud. Right? They interact. And when the electron clouds are facing each other very close to one another, then what happens? They repel. When they repel, this equilibrium gets disturbed. And this equilibrium gets what? Disturbed. The equilibrium gets disturbed, then naturally they get charged. And if I can draw for you, then if you basically apply pressure, they come closer, and the equilibrium disturbed. Equilibrium disturbance is basically shown like this. It is basically shown like this. Watch the equilibrium getting disturbed. All the negatives towards one side. In an atom, all these negatives have gone towards one side due to the influence of the electron cloud of the second one. Then if that is the case, then once all the negatives are here, then you can expect a positive charge to the other side. Because all the negatives have gone to the other side, so naturally this side would be positive. Similarly, here there is a repulsion, so what will happen to the other atom is a positive is there, so the negative, all the negatives here and the positives here, you must understand. Then I say the positive not in, I can simply say equilibrium got disturbed. Equilibrium got disturbed. Right? Because you have drawn them close. These electrons are actually influencing these electrons, so all towards one side. So all towards one side, this becomes positive. This will attract the negative in the second atom. And now you can see charge. You can see charges. You can actually see charges developing at high pressures. So if number of positives equal to number of negatives, it need not be positive, it need not be neutral. Number of girls and boys are same. Still the class is charged. All boys towards one side, all girls towards one side. You can see all boys towards one side, one girls towards the other side. You must understand. You got charged. So you cannot say that number of positives equal to number of negatives, the class is neutral. No. At high pressures, you can actually see. And then what happens? The positive and negative, you have forces. And that is called van der Waals force. You must understand this. That is called van der Waals force. Now, when van der Waals forces are existing, the internuclear distance between these two and make it half, this is called van der Waals radius. You must understand. That is called van der Waals radius. So, you have to do this procedure. Procedure means apply what? Pressure. Till you get what? Van der Waals force. And a force existing will be a force will be existing only when you have a negative charge and a positive charge. And for a neutral atom, you can also have charged, provided if they are very close and the electron clouds are interacting with one another. My appeal to all of you is follow me, follow Tone Academy, follow T1 channel, bank on us, because we will be following the sequence, and every subtopic I'll be linking this to the JEE or the pre-engineering test. So just relax at any point of time, just to click on the T1 channel, Tone Academy, subscribe, and I'll be there. Along with me, we host the best faculty available for you. Thank you, and thanks for listening.